So today I'm going to talk about searching for singularities in Navier-Stokes flows. So this work is done with Bartek, my postdoc supervisor, and Dongfang, who's Bartek's former postdoc, and Diego Ayala, who's Bartek's former PhD student, and Charles Darwin from University of Michigan. So today I'm going to first take a look at the general overview of a regularity problem for Navier-Stokes, and then a quick review for the 1D Burgers equation and the 2D Navier-Stokes equations. Then we're going to talk about the growth of entropy in 3D Navier-Stokes flows. So for this part, first we are going to take a look at the instantaneous problem, and then we're going to talk about the maximum growth of entropy in finite time problem. So I'll give the detailed definition of these problems later in the first section. Okay, so here is the NeverStock system we are all very familiar with. So we are basically talking about the NeverStokes equation with the incompressibility condition, and we are solving this in periodic boundary conditions. So the dimension of a domain could be 2-dimensional or 3-dimensional. And we have a big question, which is given the smooth initial condition U0, does the NeverStock system always admit smooth solution for arbitrary long time t? So this question is actually important because if the solution is not smooth, then they are not physically meaningful. And the importance of this problem can be seen from it states as one of the millennium problem from the Clays Institute. So if people can solve this problem, there's a $1 million prize for this. Okay, so let's take a look what could go wrong with the solutions to Navier-Stokes equations. So let's take a curl to the original Navier-Stokes equation, then we can get this verticity formulation. Omega is defined as the curl, and that is the verticity. So from this, we can see that there's a nonlinear term on the right-hand side, which is the vortex stretching term. So it's written as a grad u dot with omega. But if we write omega as a gradient of the inverse Laplacian, then we can use this kernel to write u as in form of omega. Then we can see that there is a quadratic source term up here for d omega dt. So it's basically d omega dt equals to something plus this quadratic source term. So we can compare this equation with several very simple models. First, we can take a look at this very simple ODE model, dy dt equals y squared with the initial condition. So this is very easy to solve, and we know that we have a blow up at the finite time t equals to t0, which t0 is given by 1 over y0. So we can see that actually the equation is not satisfied at t equals to t0. And if we start from initial data, then the solution is not defined for t greater than t0. So here we can see that we have a singularity in L2 sense. And then another simple example is the inviscid Burgers equation. We can see that this is probably more familiar with the Navier-Stokes equation. We can see we have ut plus u times ux equal to 0 with a given initial condition. And this Burgers equation can be solved to get this implicit equation. And we know that if we have this initial condition phi x like this, then there will be a shock wave appeared at the finite time t0. And this t0 can be measured by the minimum of derivative of initial condition. So we can see that at finite time, then there will be a shock wave. And then we can say that the equation is not satisfied at t equals to t0. And the solution is not defined in classical sense for t greater than or equals to t0. So actually, a weak solution may be defined for t greater than or equals to t0, but not in the classical sense. Okay, now we can go back to take a look at this Navier-Stokes equation. So again, the importance is because if the solution can become singular, so either in as a blow up in the velocity field or the Sobolev norm blows up, then the Navier-Stokes system is not a correct model because the solution is not meaningful in physics. Then actually we should amend this Navier-Stokes equation by modifying the viscous term. So for 2D case, actually, people already have the existence theory complete. So people already showed that smooth and unique solution exists for arbitrary times and for arbitrary large data. But for 3D case, this question still remains open. So people can only construct weak solutions for arbitrary times, and the people can only show that classical solutions exist for finite time. So finite time locally in time only. But people cannot, but we don't know whether there's a possibility for Blowup for arbitrary large finite time. So there's still possible for finite time singularity. The method to study this problem is that we want to use the regularity, conditional regularity results. This means that instead of checking the smoothness of solutions directly, we use an equivalent result, which is the bounded of entropy. Entropy is a very important quantity which defined here as the integral of curl of U squared. So basically verticity squared. And in periodic domains, it can also be written as this form. So then because there's equivalence between smoothness of solutions and the bounding of entrophies, actually our question can be rephrased as if the maximum of entropy stays finite. Actually, if there is a blowup for entropy, then we can say that there's a blowup for the solutions. So the way we do this, the first idea is can we estimate this growth rate of entropy dEdt using some subglyph embeddings, some inequalities to get this. So the estimation usually looks like this. So this is the bounds on the rate of growth. The general form is that dEdt is bounded by C, a constant, times the entropy to the power alpha. Alpha is indicates the power of exponents and always depends on dimensions. So from this equation, we can see that if alpha is less than or equals to 1, then we can see the entropy actually is bounded by an exponential equation, the exponential function. So it's finite in time. But actually, we can improve this result a little bit by using this energy equation. So let's use kT to denote the kinetic energy, and we can find the relation between energy and entropy as a dk dt equals to -2 nu times entropy. So basically, entropy tells us the dissipation rate of energy. And after we have this formula, and we can use the ground-Wolf inequality to get a better result, which is if alpha is less than or equals to 2, then actually we can prove that the entropy is bounded for finite time at finite time. But when alpha is greater than 2, actually we cannot find a finite estimation about this entropy. Okay, then we can take a look at a 2D case. The best estimation we can get for 2D Navier-Stokes flows is that the growth rate for entropy is bounded by a constant times entropy squared. So using the results we just mentioned, we can say that the entropy is bounded for finite time, for arbitrary finite time, and then we can say that a smooth solution exists for all times. So that's the reason why we say that the 2D problem is already closed. We already have the complete existing results. But actually for 3D case, things becomes complicated because now the alpha equals to 3 in this estimation. So in this parallel estimation, we get dEdt less than or equals to constant times et cubed. So as a result, corresponding estimate is not available. And we can only say that the ET is bounded by the right-hand side, and the right-hand side blow up at a finite time. So as a result, we cannot say the singularity in finite time cannot be ruled out. Of course, this doesn't mean that we do have a singularity. We still need to search for this, right? So one way to find out this question is to see whether we can make this estimation better. So we want to know whether this estimation is sharp. So the first problem, which is the question 1, is that we want to check the sharpness of this instantaneous estimation. So we want to maximize the instantaneous growth rate dEdt. So this is for 1D and 3D case. For 2D case, because the question is already solved, we consider another quantity, which is the P, or the plane entropy, to discuss this question. So for the small question, the question 1, we discussed the instantaneous estimation. And then if this cannot solve the question, we want to go to the question 2, which is the finite time question. So you can see that for this question, we want to find out the largest entropy can be achieved at time 0 to t. And instead of talking about the growth rate, we actually talk about the quantity, the value of the entropy enough. So this is the estimates we have for right now. 1D, we consider the Burger's equation. And for 2D and 3D, we consider the Navier-Stokes equation. And for 1D and 3D cases, we use entropy as the quantity we want to study. And for 2D Navier-Stokes flows, because the entropy is not interested, we use the plentropy instead. OK, and our question is whether these estimations are sharp. OK, so now let's first take a quick review about the 1D Burger's equation and 2D Navier-Stokes equation. So now we have this viscous Burger's equation in 1D, and we have the periodic boundary conditions. The instantaneous and the finite time problems are stated as follows. We want to maximize either the dt, the growth rate, or et at finite time. OK, so let's first take a look at the instantaneous problem. The growth of entropy can be written in this form, and after applying some inequalities, Sobolev inequalities and Young's inequalities, we can get these estimations. So you can see that this is in the form of d dt is bounded by c, a constant, times et to the power alpha. And now the alpha is given by 5/3. So although it's less than 2, but we still want to see the whether this estimation is sharp. So our question is, can we actually find solutions which saturate this given estimate? And we want to use gradient flow method to approach the optima. So this is the result from Lu in 2006. So actually, they even found an explicit solution for the extreme entropy growth rate. And they have the power given by d dt equals to constant times e to the power this one. So we can see that it's basically 5/3. So we can compare with the analytical bound and say that actually this estimation is sharp, and we cannot improve alpha anymore. This is the figure showing the comparison between the analytical results and the numerical results. The dashed line above here actually is the Sobolev bound with alpha equals to 5/3, and there are several lines beneath it. The plus sign provides us the numerical results from the gradient flow, and the solid line actually is the exact solution described here. So we can see that although the constant multiplied before the exponential term may vary, so we can see that here is 0.9 something, but here we have 3.2 something in the analytical bound. But actually, they have the same slope, which means that we cannot improve the power. We cannot prove 5/3. So we have the sharp estimation. And then we can talk about the finite time problem. So we want to maximize this entropy. So we want to maximize E of t for arbitrary long time, t greater than 0. But actually, there's a difficulty is that if we want to maximize with respect to time, then the function, this operator, is not differentiable. So computationally, it's very difficult to do. So instead, what we do is we fix the time capital T. So we want to maximize the entropy at a fixed time capital T, and then we can vary T to do different computations. So because this is computationally more easy to do. So analytically, we have this estimation. The maximum of entropy is bounded by this form, and as E0 goes to infinity, we can see that this is approximately E0 to the power 3. But actually, for the instantaneous, but actually for the numerical optimizer, the best growth rate we can see is that as E0 goes to infinity, this follows the E0 to the power 1.5. So basically, half of the alpha we get in the analytical estimation. This means that the analytical estimation here is not sharp as E0 approaches infinity. And we also use the gradient flow method here, and the details of this algorithm will be introduced when we talk about the 3D problems. Okay, then let's take a quick look at the 2D problem. So for 2D problem, if we take a look at the verticity equation, actually, we can show that the entropy is not increased because the time derivative actually is decreasing. This is because if we think about the vertex stretching term, which is omega dot product with gradient u, then because gradient u is actually two-dimensional and the omega is along the third dimensional, actually they are perpendicular to each other. So the vertex stretching term disappears in the 2D equation. So also we can show that the smooth solution exists for all times. So then in order to observe some stretching phenomena, instead of looking at this vorticity equation, we consider the vorticity gradient. So we take a gradient along at the vorticity equation to get this. Now we have the new stretching term, which is the gradient of omega dot with gradient u. And using this, we can define this polynstrophy as this. And we can consider the estimation, instantaneous estimation for polynstrophy and the finite time growth for polynstrophy. So here we have two analytical estimations for dp/dt. One is by During and one is by Ayala. The difference between this one and the entropy one is that the entropy one only have a single variable, single quantity on the right-hand side. But here we can see that there is a polynstrophy on the right-hand side, of course, but there's one more quantity, either entropy or energy involved. Also, we have this finite time bound. The maximum of polynstrophy can be bounded by this. And also we can show that, show numerically that this estimation actually are sharp. So if we go back and take a look at this table, we can see that for the first 4 questions, we know that the 1D burgers in finite time is not sharp, and the other 3 estimations are sharp. And the problem left is that whether the 3D Navier-Stokes for 3D Navier-Stokes flows, the estimations are sharp. Okay, now let's take a look at this instantaneous problem for 3D Navier-Stokes equation. So again, this is the Navier-Stokes equation. We solve this in the periodic domains, and we consider the max ddt problem with the incompressible condition. So our analytical estimation is growth rate is bounded by a constant times ET cubed. And this is the numerical approach got from this Lu and Doran's paper. Actually, they find 2 branches, and for the upper branch, actually, the growth rate is given by E0 to the power 2.997. So basically means that the analytical estimation is sharp. And the vorticity field is actually given by this double ring structure. We can see that there's 2 rings here, and the curves are the vortex lines. Okay, so if we take a look at this rate of growth of entropy, we have this sharp estimation. We know that the dt is bounded by e to the 3, and we cannot improve this 3 anymore. So from here, we can see that the corresponding finite time estimate will blow up at t star, given by this. So, of course, we need to consider the finite time problem to find out the maximum of entropy. But before that, we can take a look at the structure of the instantaneous optimizer. At the limit of E0 approaches 0, the optimal state could be found analytically, because that's just the eigenfunctions for vector Laplacian. Here, we have the 3 different eigenfunctions. And the first one actually corresponding to the largest growth of ddt. And the third one is the famous Taylor and Green vertex, which are first described by Taylor and Green in year 1937. And also here are the vertex for maximizers. We plot the magnitude of vertex in these figures, and we can see that when E0 is moderate and large, we can see that we have this classical double ring structure. We have two rings in pairs. And as E0 becomes larger and larger, we can see that these rings are more and more localized. We can see that actually they're more and more smaller and smaller. But when E0 is very small, we can see that the ring structure becomes torch, and we have some different structures like this. When E0 is very small, we have the limit as E0 goes to 0, we can see this structure. Okay, and here shows the time evolution for E0 equals to 100. The initial is the double ring structure, and we can see that as time going, this double ring structure basically preserved, but becomes less and less localized. So the ring becomes bigger and bigger. And this is the time evolution for using this initial condition. And if we take a look at the entropy with respect to time, we can see that here we compare three different initial data. The blue one is the extreme one using the instantaneous optimizer, and the black dashed one is the Taylor-Green vertex, and the red one is the Kita-Platts vertex, which is another famous vertex structure. We can see that initially, of course, the blue one is the biggest one because this is the results for the instantaneous optimizer. But for a larger time, we can see that the Taylor-Green one actually has a larger entropy compared to the extreme initial data. This is because the relation between energy and entropy. We know that entropy can be understood as the dissipation rate as kinetic energy. And if the entropy is very large at the beginning time, this means that the energy decay very fast at the beginning time. And basically, in a very short time, the energy will go to 0 and everything dies out. And as a result, the entropy will decay very fast here. So this gives us an idea that for blowup to occur, actually, we need alpha becomes greater than 2 and less than or equal to 3. And here, for the extreme state, for the instantaneous problem, we know that we have these pairs of vortex rings. But if we want, we want to seek for finite time blowup, the previous computation tells us that actually alpha equals to 3 may not be a good choice because the energy will dissipate very fast. So actually, we want to construct a sub-extreme vortex state. And the alpha is greater than 2, but less than 3. And we want to seek for such initial conditions that can provide us a very big growth of entropy in finite time. Okay, and this leads us to this finite time problem. So we want to maximize the growth rate, the growth of entropy over finite time t. So again, we choose E0 as the initial constraint, and we choose finite time t. So we want to maximize the entropy at the ending time u at t, and the ut, of course, is the solution to this NeverStock equation. So the reason we want to use this is, again, similar to the 1D Burgers equation. If we want to maximize over time, then the operator is not differentiable, and the computation is very difficult to deal with. So here we choose our finite time before. Okay, so the algorithm we use is this gradient flow method. We use UN+1 as the initial data at the N+1 iteration. And this is obtained by starting from the nth iteration and plus this tau n times gradient flow. So gradient ET is actually the increasing direction, and tau n is the optimal step size can be computed by arc minimization. And this P actually is a projection on the constraint manifold. Basically, this is the normalization with respect to the entropy. So we want to fix the entropy, initial entropy to be E0. And the divergent-free method actually condition is satisfied automatically. Okay, so the question now is how to compute this grad ET, how to compute the gradient flow direction. And to compute this, we introduce this adjoint system. So we can see that this adjoint system used the information for U, which U is the solution to the original Navier-Stokes equation. And the reason we use this is here. So in order to compute this gradient direction, we can first use Riesz representation theorem to represent our Gauss derivative in terms of gradient. And we want the term we want to compute, we want to seek for is this gradient in H1 norm. But actually, it's easier to compute this gradient in L2 norm using the adjoint system. The L2 gradient actually is the initial state for the adjoint system. So if we go back to look at this adjoint system again, we can see that first we can solve the Navier-Stokes equation forward in time to get the velocity field U, and we save this U. And then we solve this adjoint system. And we can see that the initial condition for this adjoint system is given by at final time t. So basically, we solve this adjoint system backwardly using this initial condition and use the information we get from the forward Navier-Stokes equation. And then finally, we can get the U star at time t. And this time, this U star at time t actually provides us the gradient direction in L2 sense. The next step is we can transfer this gradient direction in L2 sense to the gradient in H1. And here we use the L1, which L1 is the length scale in Sobolev norm. So in a short conclusion, the computational algorithm is as follows. First, we choose the initial entropy E0 and the initial time window T. And then we can provide the initial guess. So usually this initial data is provided using a continuation of, for example, smaller E0 or smaller T. But if we do not have previous initial data, then we can use the instantaneous optimizer as the initial data. And then we solve the Navier-Stokes system, and then we solve this adjoint Navier-Stokes system backward in time. And then after we get this U star at 0, we get this gradient in L2. And then after we solve this elliptical equation, we can get the gradient in H1, which is what we want. And then last step is to find out the optimal time step tau n by solving this arc minimization problem. And then after we take this projection, we can get a new initial guess. Okay, so we'll run this iteration until it converges, and then we can finish this optimization problem. So this is the results for E0 equals to 50. We choose E0 equals to 50, and we choose different time window t equals to 0.2, 0.3, and 0.4. So we can see that these three red curves corresponding to the results for t equals to 0.2, 0.3, and 0.4. And we can see that the 0.3 one is actually the thickest one because it actually achieves the highest value of entropy here. We can see that when capital T is smaller than 0.3, it keeps increasing for the entropy. But if capital T is greater than 0.3, we can see that at the end time, it starts to decrease. But at the optimal time for T equals to 0.3, we can see that actually it stays flat, which means that we just achieve the highest point here as capital T equals to 0.3. And we can also compare these three results with the instantaneous optimizer. The blue dashed curve is obtained using the previous instantaneous optimizer. We can see that at a very short time, the growth is very fast because it maximizes DEDT, but then it decreases very rapidly because the energy basically dissipates. And then if we take a look at the red ones, we can see that initially the entropy is not increasing very fast. And for one of them, for the last one, you can see that it even decreased at the initial time. And then we can see that because the energy is preserved, we can see that for larger time, the entropy grows very fast. So this is the difference between the time evolution of entropies using the different initial data. And we also observed two different branches So we use E0, the initial entropy equals to 100 as an example, and the corresponding optimal time is given by 0.27. So the left part is the one branch in the symmetry, and symmetry is in the sense that if we consider 3 component-wise entropy, then actually they are all similar, they are all the same, and they equals to 1/3, exactly 1/3 of the total symmetry, the total entropy. So this is the symmetry branch. But for asymmetry branch, we can see that the component-wise entropy are not equal. And we can see first the blue one is bigger, and then the pink one, the pink dash one is bigger. So it's an asymmetry. We can say that when E0 is less than 100 for small entropy case, then the symmetry branch is more pronounced, is dominates. But when E0 is greater than 100 for larger entropy case, actually the asymmetry branch will dominate. Because we are using a gradient flow method, so for Euro E0, for Euro initial entropy values, it's hard to catch both branches because it's easy to slice to the higher branch. But for E0 equals to 100, this is the part that the 2 branches are very close to each other, so we can get 2 branches simultaneously. Okay, so this is the structure for the different branches. We can see the first one actually is the structure for the instantaneous optimizer. We can see that it's very localized, and also we have this double ring structure, pairing ring structure. For symmetry one, of course, compared to the instantaneous one, is much less localized. It's very big. And we can see that the structure is a symmetry. The white curve here is actually the vertex lines, and it's like a circle shape. For the asymmetry branch, we can see that it's more like a cylindrical pair of cylinders. So it's obviously not symmetry in 3 directions. And we can also see that the vertex lines, the white curve actually performs differently. Yeah, so yeah, it's less localized compared to the instantaneous ones. Okay, so if we combine all the results together, we'll get these data sets. Basically, 1 point in the figure corresponding to 1 curve we showed before. So we collect for a certain time and for a certain entropy, we collect the maximized entropy here to build this figure. For each branch here, corresponding to the fixed initial entropy E0 for different time window t. And the blue points corresponding to the symmetry branch, and the red curves corresponding to the asymmetry branch. We can see that for lower entropy, for the entropy less than 100, the symmetry branch is shown because they dominate. And here is the case for E0 equals to 100. So we say symmetry branch and the asymmetry branch at the same time. And for E0 greater than 100, the asymmetry branch will dominate, and here we only show the asymmetry branch. So computationally, it's very costly, and we use the parallel. We use the MPI in Fortune 90 to compute these data sets, and we put the codes into the computer candidate clusters to run the computations, and for each single point, for each single data point is cost about dozens of hours on either 32, 64, or even 128 cores. So if we catch the highest point in each branch, then we take the maximize over time. We can get the maximized entropy that depends on the initial entropy. So the data is shown as this. We can see that for the left curve, figure shows the blue and red curves. The blue curve is basically follows the linear form because it's still in the low entropy regime. But for the right figure, we plot in the logarithm scale, so we can see that it satisfies a power law. So if we collect all the data sets and consider the maximized entropy, then we can find out that the max ET actually follows the power law, which the power is given by E0 to the power approximately 1.5. So this is actually a very interesting result, because this shows that the growth rate of entropy is actually not that fast, right? Because then we can see here that entropy seems to keep finite in finite time. Now we can take a look at the structure of different optimal initial data. This is for E0 equals to 500, and the corresponding optimum time is 0.17. And if we take a look at here, we can see that along different directions, we have this pair of vortex cylinders in different directions. So they, in each direction, actually is very clear, but if we combine them together, we have this polygon-shaped vertex structure. And here, let's take a look at the time evolution of the extreme flow for E0 equals to 500. Okay, so this is the time evolution of the vertex in 3 directions. So we use red, blue, and green to denote 3 vertex direction components. And because this animation is made using fixed color bar, so because the rapid increase of entropy, we can see that initially it's hard to see anything. There's even no green appears, because it's weak compared to the later time. But then, as time going, we can see that we have more and more vortex appears, and now we can see that the green first shows, and the red one and blue one starts to intersect each other. And then as time going, there's much more and more small structures appears, and eventually we can see that it's very complicated. So we can go back to here to see that actually in each direction we have a vertex tube, and there's results for vertex tube that we have there might be reconnections. And here actually we can clearly see there's reconnections in this 3D 3D flows. First, we can take a look at this components-wise the entropy. Initially, we can see that the dotted line is the highest one, and then the solid line, and then the dashed lines, right? And then at the time approximately equals to 0.06, we can see that the lower 2 lines actually intersect, and then they intersect with the upper dotted lines. And then as time going, we can see that their order reversed several times, and at the final time, dotted lines wins again, and actually the other 2 lines basically they are the same. So you can see that the order between these 2 component-wise, the entropy changed several times, and this is a clear evidence for reconnection. And here is the vertex line for t equals to 0.09. We can see that the white curves actually are the vertex lines that's near the reconnection point. We can see that there are 4 branches, and they seems to reconnection right now. And the blue regions are the regions which is the vertex is very small, is close to 0. You can see that it's a very localized, very localized reconnection, and clearly see this. So we can go back to this animation and see this again. And starts here, we can see that things becomes complicated. And actually, the reconnection occur at this time. And there's several reverse of orders between these 3 component-wise entropy. And during this process, we can see that the small structures appears, and the estimation becomes this becomes a very complicated range. Okay, so finally, we can take a look at the growth rate of entropy. So the blue curves corresponding to the growth rate for the extreme trajectories with the extreme initial condition. And this red curve is tell us the slope for e to the power 3. We can see that, of course, each blue curve is under this red curve, is under the bound. And the growth rate, if we take a look at a single branch, we can see that only for a middle region, the growth rate is large, because for larger region and for small region, the growth rate is small compared to the entropy. And actually, even in this case, we can see that the growth rate is approximately e to the power 0.85. So it's a suboptimal in the sense of instantaneous optimizing problem. Okay, so as a conclusion, for the 2D case, we know that the instantaneous estimations are sharp in the planimetry quantity. And in 2D, we know that actually the entropy is not interesting because it's bounded anyway. And the regularity problem in 2D actually is complete. But for 3D problem, the instantaneous estimation are also sharp, which is with the power given by 3. But because of the immediate depletion, then the entropy growth is very weak. So if we want to seek for a large growth of entropy, we don't want to choose this instantaneous initial condition. And if we want to maximize this growth of entropy in finite time, we can find out that the scale actually is proportional to E0 to the power 3/2 as E0 becomes large. And as a result, we can see that even in such worst case scenario, there is no evidence for formation of a finite time singularity. And we can also see from the animation and from the figure that the extreme behavior is realized by a series of reconnection events. And what's interesting is that actually this power 3/2 is the same as the Burger's equation. So at the beginning of this talk, we can see that the Burger's equation actually follows this 3/2 power. So this means that actually the entropy growth for NeverStock's equation, for 3D NeverStock's equation, is not faster than the 1D Burger's equation. So actually, in the sense of magnitude, actually they are similar. Okay, this is the final table. We already fill all the blanks. We can see that for 3D NeverStock equations, the instantaneous estimation is sharp, but the finite time estimation is not sharp. It follows the power law given by the power 3/2. And right now, the ongoing work we are doing is considering more general conditional regularity results, which is this Lajinskaya-Potisari family of conditions. In this series of conditions, we consider the Lajinskaya-Potisari norm, which is LQ in space and LP in time, and P and Q satisfy this inequality. And the conditional regularity result states that if this LPS norm keeps finite, then the solution to the NeverStock's equation is also smooth. So this is another big family of results we can discuss. And there are also several related works, for example, the extreme behavior with the consideration of noises and the sharpness of estimations for other systems and the maximum entropy growth on bounded domains. So right now we are all talking about periodic domains, but it's also interested in bounded domains. Also, the extreme behavior in 3D Euler flows is also remains as an open problem. And here are all the references, and thank you for hearing.
There's a couple of questions in the chat.
Oh, let me take a look.
If you wanna.
How I can see the chat here?
If you go on the bottom, there should be the chat tab. Like if you just have the Zoom window open.
Yes, yes. Oh, here. how accuracy is the quadratic rule for computational entropy in the singular. Okay. So about the accuracy of the quadratic rule, actually, we use the time step basically given varying from 0.10 to the -3 to 10 to the -4. And on the space, we use resolution varying from 128 to 512. And actually, we carefully check the spectra to make sure that it's well resolved. So, and also because we can see that the entropy basically becomes bounded. So I think it's we can make sure that it's pretty accurate. And do optimal U for different initial entropy share certain similarity? No, actually, the optimal U, the shape of optimal U changes due to different entropy. So let me see. We can see that for E0 equals to 100, the optimal entropy shows like this. So you can see that there's basically two cylinders appears, but for larger cases, although the combined entropy is not shown, but here actually we can see three different vertex tubes. And if we take a look at the combined one, it's different from the previous one. And also, I think for very large entropy, the structure are similar, but for small ones, they are quite different. And the change of entropy in time sequence. Actually, if we take a look at this figure, the change of entropy in time, I'm not sure if you talk about this maximized ones or a single branch.
The last figure you show in the.
Oh, yes. This one.
Yes.
Okay. Okay. This one is because this is drawn for dEdt with respect to E. So basically, if we take a look at this max ET problem, it's always start as a low level and increase very slow, and then we have a rapid increase, and then we reach the maximum. So if we take a look at here, for example, we can see that the growth basically occurs at this part, and this part show us the maximum growth of entropy. And at the beginning part and the end parts, they are all the growth rate is very small. That's the reason why when we take a look at the last figure, in the middle, it's big, and at the two ends, they are small, because this is plotted for dEdt over versus E.
Thanks.
Thank you.
Yeah. Thank you, Dee, for a really excellent talk. I had a few questions.
Sure.
One which I think this aspect that the instantaneous growth is the colliding vortex rings, like the axisymmetric swirl-free structure, but that doesn't maximize in time is very interesting, because there's been a lot of focus on this in the literature as sort of a maximal case, but it's known to be smooth, which sort of suggests that the initial maximizer is more about Sobolev, like maximizing certain Sobolev inequalities, than it is really about the underlying like turbulent fluid structure. Sort of the question I have is there a point where there's symmetry breaking in the sense that, like, for very short times, it would be, you would expect that the rings will still be the maximizers, right? Because they're the instantaneous maximizers. And for some like very small time epsilon. So I'm curious, like, when does that sort of branch off?
I see. Yes, I think we can understand the instantaneous optimizer as the max ET problem as t goes to 0. And for the symmetry breaking problem, if the symmetry means the symmetry between different component-wise entropy, like in this one, then because this is a more like a global effect, because the jump between branches is hard to see the reason why the jump between one branch to the other branch, because they just seek for the higher value of entropy. So it's hard to see. But if we talk about the entropy constraint, then it seems like for sufficiently large entropy, then it seems it becomes asymmetry right after for very short time. So I think it happens instantaneously.
And I guess just one other question is sort of the role of the torus seems to be playing a kind of the torus seems to be playing a kind of non-trivial role here. And so I was curious, some intuition on that, because sort of in the instantaneous case, for large entropy, you're just zooming in. And so that's sort of like, you could extend that to 3 dimensions. If it's localized, the torus, you don't really see the boundary, right? So if the torus, the whole space is no different. But sort of in the whole space, the entropy is just a scaling parameter. You can sort of reduce everything to initial entropy 1 and you get everything else out of scaling. But here there's like different qualitative behavior at different levels. And so that's something I'm sort of curious about.
Yeah, I think so. I think the phenomenon between unbounded domain and the bounded domain are quite different because here entropy plays a very important role, but in that case, in the bounded case, actually that's not that important.
All right, I don't want to monopolize too much time. Does anyone else have any questions? Rudy?
I have one, very simple question. In one dimension, when you were, working on Burger's type equations, how does one define entropy for a 1D flow?
For entropy, we just define the entropy as a gradient of U. I think the definition is similar. It's just the E is defined as integral of curl of U itself. So it's just the H1, basically, the H1 seminar.
But there's no curl in one-dimensional flow, right? So there's no vorticity. So it's just a gradient of U
I think so.
Squared.
Yes.
Okay, so I just wanted to be clear on that.
All right, well, there's no other questions. Let's thank you again for a great talk.